Good day, everyone, and we are back again together looking at the IEB November 2018 paper. So, for those of you who haven't subscribed, please do the right thing. And please tell more people that, we even trying to assist as the IB is preparing, or IB candidates rather, are preparing for their final exam this coming week. So, we're going to look at question 3 from the 2018 paper. All right, and for those of you who need assistance with mathematics or physical science, please don't hesitate to just send us an email. Our email address is info@mlungisinkosi.co.za. All right, so let's look at this question together. So we're given the velocity versus time graph that shows the motion of two different objects sliding in a straight line across a horizontal surface. Right. So before we even go into the questions, all right. So first of all, assuming that we've got these, of course, we've given two objects. And if you look at this one, you can see that definitely that velocity is positive, first of all, and it's increasing in the positive direction. So if you were to take a particular direction, let's say for velocity, just for argument's sake, let's just say it was moving to the right. So it means that in that case, it's increasing. The velocity, the speed is increasing towards the right. Okay. And you can see that velocity is increasing there. Right. But if you look at this particular object, so first of all, you can see that the velocity is negative, meaning that it's moving in the opposite direction. Okay, first of all, and it has a decreasing speed. Now note, the velocity is negative. It's telling you that it's in the opposite direction, but at the same time, it's telling you that it keeps decreasing in the opposite direction. Now, the first question that they ask us is, could friction be the cause of the change of the velocity of object K, which is this one? Now, if you think about that question, what would friction do? Friction would cause an object to actually slow down, right? But if you look at object K is actually increasing in velocity. So as a result, friction couldn't be the cause, right? So you can just simply mention there that, first of all, the velocity is increasing, all right, in the positive direction. And in this case, it means that your net force is actually in the positive direction, okay? That would be, and by the way, if your net force was due to friction, it would be actually in the negative direction, isn't it? Okay, so that could be your explanation there. You could say, well, definitely it's not due to friction, right? And the explanation is that the acceleration is positive, and as a result, the net force is also positive. Okay, right. So they say, could friction be the cause of the change in the velocity for object L? They say answer yes or no. Now think about object L. What's happening with object L? We said that this velocity is decreasing. How do I know that? Suppose you had a value here. Let's say for argument's sake it's 10, right? It would be negative 10. I agree, but look at this. What happens as time progresses? In this case, it would mean that speed would actually be getting less and less. Okay. Now, it doesn't matter that it's in the negative direction. All it's telling us is that it's actually in the opposite direction, right? So what we are simply gathering from this is that the velocity is decreasing, and in this case, it could be due to friction, right? So the answer to that is yes. Okay. Right. Now let's get to question 3.2. They say we've got a hailstone of mass 0.7 kilograms, okay, that falls from rest from the top of a cloud. Okay, so I'm going to just make a drawing there. Okay, so suppose here's our lovely cloud. Okay, so there it is there. Okay, so now I'm going to have a hailstone. So in this case, there's our hailstone. They say it's dropping. So in this case, we know that the mass of this guy is 0.7 kilograms. Okay, and they said that we are dropping it from rest. Okay, so there's our hailstone. We know that the initial velocity is 0. So I'm trying to populate as much information as I possibly can, right? So that I can answer the questions. So this is 0 meters per second. Okay, and now they say to us the average acceleration of the hailstone while falling through the air is 0.21. So we know it's experiencing an acceleration of 0.21 meters per second squared, and of course that's downwards. Okay, so what I'm immediately going to do is I'm going to choose a positive direction. If you'll allow me, I'll just take positive as downwards as positive. So now they say to us the hailstone reaches the ground at a speed of 34 meters per second. So in this case, we get to the ground somewhere there at 34 meters per second. Okay, so let's have a look at the question that we are asked. So first of all, they say define acceleration. So the definition of acceleration, remember, you can just get that definition from the equation change in velocity divided by change in time, and we know that acceleration is the rate of change in velocity. Okay, so acceleration is the rate of change in velocity. As I calculate the distance of the stone traveled, calculate the distance the hailstone traveled from the top of the storm cloud to the ground. So we want to find out. Okay, so if we call that position A and that position B, we know that our initial velocity was 0, our final velocity was 34. We know that the acceleration was 0.21, and what we want to find out is the displacement. So in this case, I'm just simply going to take now if you think about equations of motion, what are we not given here? We're not given time, right? So I'm going to go for the only equation that is without time. And by the way, you could have easily, if you had time, you could have easily have gone for this one, but we don't have time, right? So in this case, for 3.2.2, I'm going to simply say, okay, so vf squared, or v squared rather, is equals to u squared plus 2as. So or you can even use vf squared is equals to vi squared plus 2a delta x if you want to. Okay, so what is my final velocity? It's 34 meters per second squared, but remember that's positive because it was going downwards, and we've chosen down as positive. Our initial velocity was 0. Okay, our acceleration was given to us as 0.21. Okay, and they wanted the distance. And by the way, there was nothing wrong. You could easily have found the equation, the subject made s the subject of the formula. So in this case, that's going to 34 squared divided by 2 times 0.21. So let's see, divided by 2 times 0.21, and in this case I get a distance of 121 0.38 meters. Okay, so it means that the distance that it fell there was a distance of 121.38 meters. Right, moving right along, they say falling objects normally have an acceleration of 9.8 meters per second squared. They say explain why the acceleration of the hailstone is much less. Of course, in this particular case, they did not tell us to ignore the effects of friction. So, if you think about a practical situation where you've got a falling object, okay, so in this case, it would obviously be fighting against air friction, right? So it could be due to the presence of air friction. Okay, So let's go to the next one. They say on reaching the ground, okay, they say on reaching the ground, rather, the hailstone pierces rather 12 centimeters into the ground before coming to rest. Now I want you to just think about it there. We get to the ground. Now I'm just going to try and draw it there. Suppose this is our ground and the hailstone goes into the ground. Now think about it. It would pierce through the ground and it would reach a depth there on the ground of 12 centimeters, right? That's what they said to us. So the distance between there and there is 12 centimeters. Okay, so what we want to find in this case, they say calculate the acceleration of the hailstone while piercing the ground. Now, remember, it arrived at this point here at 34 meters per second, right? And what do I know? The velocity at this point here, my velocity would be 0, okay? And we've got that little distance there, 12 centimeters. But remember, once we say centi, we need to now convert it to meters, which in this case, we are going to just divide by 100. Just remember that when you say centi, just think every time you say percent, okay, or every time you say cent, it's always a hundredth, right? Meaning that you divide by 100. Right, so I'm going to say, right, we're looking for the acceleration. So I've got initial velocity, I've got final velocity, I've got distance, and I'm looking for the acceleration. And we're going to use the very same equation of motion. So I'm going to say v squared is equals to u squared plus 2as. By the way, this is 3.2.4, right? So v squared is equals to u squared plus 2as. Our final velocity this time around was 0. Our initial velocity in this case was 34, positive 34 by the way, 34 squared plus 2 times. Now we are looking for the acceleration. Remember, the moment it pierces through the ground, because the ground also exerts a force on the hailstone, it's not going to be the same acceleration as when it was falling there, right? So as a result, my distance in this case is 12 centimeters. I divide that by 100, and in this case I'm going to get 0.12. okay, right? So in this case, let's find that acceleration. If I take 34 squared to the other side, it becomes so I have 34 squared, okay, which is 1156, but it becomes negative if I take it to the other side, and I'll divide by, so I've got minus 1156, and 2 times 0.12 is 0.24a, so we can divide both sides by 0.24, and in this case, what do I have? Divide that by 0.24, and I get an acceleration. It's a massive acceleration. And I mean, think about it. To stop a hailstone that was moving at such a high speed in such a short distance, you would actually need a big amount of force. And of course, it means that deceleration, in a sense, was actually very high. Right, so that's minus 4,816.67 meters per second squared. Right, so you can verify that for me and see if you arrive at the same answer. Okay, so now the last portion of it, okay, they say hence. So remember, every time they say hence, it means that you need to use what you had previously to then determine what is being asked. So in 3.2.5, so they say to us, hence calculate the magnitude of the force that the ground exerts on the hailstone. I'm going to park a little bit because we need to talk about what happens at that point there. Now remember what's actually happening here, right? So we are looking at two things. One, the hailstone, the moment that it actually hits the ground there, there's not just the force of gravity, meaning the earth pulling it down, okay, and there's no longer air friction, remember that, because it's not in the air, right? But the ground is now exerting a force upwards. So now it means that the force that the ground exerts upwards is bigger, right, at that particular moment than the force of gravity going down, and that's what slows the thing down, isn't it? Okay, so this is the force that the ground exerts, and this is the force of gravity, or let's rather put it and say this is the weight. Okay, so those are the two forces that are acting on this hailstone, right? So they said calculate the force that the ground exerts. So this is the force that we're looking for, right? Now I want you to think about it. We already have the acceleration, meaning that we can get the net force, but we can also find out what the weight is. Remember, when we calculate weight, we always say this is mass multiplied by gravitational acceleration, isn't it? So the mass of the object is 0.7. Remember, we're given that mass over there, okay, multiplied by 9.8. Okay, so we know that we multiplied that by 9.8 meters per second squared, and our weight, okay, so let's do that quickly. 0.7 multiplied by 9.8, we get a weight of 6.86. So it means that our weight was 6.86 newtons. Okay, right, now we're not interested in the weight, we want the force that is exerted by the ground. But let's now calculate the net force first, right? So we know that the net force in this case is equal to ma. But what are the forces that are acting on this hailstone, right? The net force comprises of the force that the ground exerts. Now it depends whether we want to maintain downwards as positive. Now I want you to notice this. We already had said down is positive, right, meaning that up is negative. If you think about it, when it is accelerating there, it's accelerating upwards because we got a negative acceleration there, right? So it means that it's going to be the weight of the object minus, right? Now, why am I saying it's positive? Because we said down is positive, minus the force that the ground exerts, right? The force of the ground, okay? And this is equal to ma. Now, let's get right into it. So we already have the weight. We said our weight is going to be 6.86. So there's our weight there. Okay. We want the force of the ground. Okay. And what is our mass? Our mass was 0.7. But we already had calculated the acceleration as minus 4,000. I'm just going to move this away, as minus 4,816.67. Okay, right, now let's quickly get our value over there. So we want the force that is exerted by the ground. Okay, we're just going to do some gymnastics there. 6.86, I'm going to take this value 0.7 multiplied by, so that's 0.7 multiplied by 48, or negative 4816.67. okay, get a value of 3,371.7, okay, or 67. All right, and in this case it means that the force that the ground exerts, if I take that to the other side, it becomes positive. If I take this to the other side, it also becomes positive. So I'm going to add it to that 6.86. Okay, I get a final answer. So the force that it's exerted by the ground, you can just verify it for me. Okay, I get a value of 3378.53. Okay, and that's in newtons. All right, so I hope that makes sense. All right, and that is it. When it comes to this question, we have killed it, and there it is right there. Hopefully that made sense to you. You are able to follow on. Okay. All right, and I'll see you guys next time when we do another question from the IEB, right? Just to try and assist when it comes to those. And by the way, for those of you who are doing, who are writing the DBE exam, these questions are just as relevant for you, and they are going to help you, by the way, with revising. It's a very, very great way of revising. All right, so I'll see you guys again next time. Sharp, sharp.